again, make sure that you guys are careful with the positive and negative values for the work and the heat. Bless you. It's not. Alrighty, guys. So let's go over this. If you guys are finishing up, feel free to finish up, but I want to make sure that we have enough time to get through Unit 6 quickly. Okay, so let's find the Q value. So here it says that the system absorbs 146 joules of heat. So is this number Q or W? Yeah, Q is heat. Now, if a system absorbs 140, is that going to be positive or negative? Yeah, if it absorbs, it's going to be a positive value for the Q. So that means here our internal energy, our Q value, is going to be positive 140 joules. Okay, because if you're absorbing heat, there's going to be more energy inside whatever system you're looking at, right? All right, next we're going to look at work, and it says it does 0.085 kilojoules of work. Obviously, this is going to be our W value. Now, if the system does work, is that going to be a positive value or a negative value? Who thinks positive? Who thinks negative? And kind of, yeah, so it's actually going to be negative. Okay, so think about it this way. Let's say that you are this is you, you're the system, okay? You are the system and you're doing work, okay? So actually, let's make this me. This is me. And I'm lifting all those, I'm deadlifting a lot again, okay? And I'm doing work, right? I'm using energy to lift, to deadlift all these plates, right? And so if I'm doing work, am I gonna lose energy or gain energy? Yeah, I'm gonna lose energy from my body, from the system. So it's gonna be a negative value for work here, okay? It's gonna be a negative work. So if a system does work, it's negative work, but if it has work done on it, that means it's gonna be a positive value for work. Yeah, so like if I was, I don't know, if this was me, and then let's just say, I don't know, a really buff dude came, right? And then, I'm putting way too much time into these drawings, but let's say this really buff dude with chicken legs came and then punched me really hard and I started flying, right? I would have more energy in the system, right? Because I would have the kinetic energy pushing me away, right? This looks like really demented, but anyway, yeah, so if I have work done on me, right? If I get pushed or whatnot, that means I would have more energy in my system, like not chemical energy, like energy to move stuff, but my body would have energy because it would be moving more, okay? So that would be an example of positive work, but here it's negative. Okay, but can we plug in 0.085? No, what did you guys see in here? Yeah, it's kilojoules. So we need to convert this into joules, or we need to turn this into kilojoules. So you could have done this two ways. You could have moved the decimal 3 times to the left, and then you could have gotten 85 joules. Or you could have done this where you change the 140 into kilojoules, and that would be 0.14 kilojoules plus 0.085 kilojoules, okay? Regardless of how you do it, you're going to get the same value. It's just going to be different units of measurement. And then here, you would have gotten, oh, this is negative, by the way. Sorry, guys. You would have gotten 55 joules, or you could have gotten 0.0055 kilojoules. Either way, you'll get the same value. But here, the system is going to increase in energy because even though it's doing some work, it's absorbing more work through heat or energy through heat. Okay, so just be careful with the positive and negative values. Alrighty, so let's move on to the next part. Here we're going to be looking at system and surroundings again. Now we're going to be going more into actual chemical reactions, and so you guys need to go over a little bit more vocab. Okay. So there's two terms that you guys need to know, endothermic and exothermic, okay? Endo is a prefix that means inside, okay, or in. And so when a process occurs where the system absorbs heat, it's called endothermic, okay, because it's absorbing heat. Heat is going inside. So here I have a lovely picture that I did not create. So endothermic is where it pulls energy into the system from the surroundings, okay? So the system is gaining energy in an endothermic system, but the surroundings are losing energy, okay? So I want you guys to think about that. If you touch an endothermic system, is it gonna feel hot to you or is it gonna feel cold? Okay, it's gonna feel cold, okay? And the reason why is because it's pulling in energy from the surroundings, right? So if the reaction is the system, if you touch what's going on in the reaction, it's gonna take away energy from inside from your finger or whatever is touching it. So endothermic systems, they feel cold because they're absorbing energy. Okay, they're taking energy away from you. Okay, so the opposite of that is when a system releases heat, and that's called exothermic. And exothermic are gonna feel warm, or I'll just say it feels hot. Okay, because it's giving you energy. Okay, so exothermic would be like a bomb because it's releasing energy around into the surroundings. But an endothermic reaction could be something like a cold pack, where it's pulling in energy from the surroundings into the system. The system is gaining more energy. Okay, so it's going to feel cold. Okay, so those are two terms that you'll have to know because there are different types of chemical reactions. Every chemical reaction is a bit different. Some of them will release energy, exothermic, and some of them will absorb energy. They'll be endothermic. Okay, so I'm gonna do 6.10 with you guys, and then we have two more for you guys to try. And so let's look at the directions. It says, in the following scenarios, determine if the process is endothermic or exothermic. You also need to draw the heat flow. Okay, so let's go over how to do that. So here it says an ice cube is melting on a hot day. So I'm gonna draw an ice cube, and it's a hot day, so the sun is out, right? Maybe you're at the beach, right? And then we have this random ice cube just sitting there in the sand. Okay, it says the ice cube is the system. Now, it says the ice cube is melting. Okay, so if the ice cube is melting, is it absorbing energy from the surroundings or is it releasing energy? Yeah, it's absorbing energy. The ice cube is taking in energy, right? Because the hot day around it, energy from the sun, it's going from a liquid to a solid. We know that if we go from a liquid, or sorry, solid to a liquid, I don't know what I'm talking about. It's going from a solid to a liquid. That means that it's gaining more energy. So that means that the ice cube is absorbing energy. Okay, so if it absorbs energy, is it going to be exo or endo? Yeah, this is going to be an endothermic process. Okay, so that's pretty much how you do it. Again, you need to specify what the system is, because if we say, hey, the air around the ice cube is the system, that means the system would be exothermic because it would be giving energy to the ice cube. Okay, you guys think you could try two more on your own? All right, so I'll give you guys a minute and a half. You can work with the person around you. Your pictures don't need to be super detailed. You can just kind of label things with like circles and squares and whatnot. But I want you guys to try 6:11 and 6:12. Okay. Maybe about 20 more seconds. Yeah, so 1, 2, 3, 4, 5, 6. Nothing on this side. Alrighty, guys. So let's go over this. Hopefully it wasn't too bad. So 611, firework explodes in the air at Disneyland. So we're at Disneyland. We have that castle, right? Right, and then we have the fireworks blowing up. This is the fireworks. Woo! And there's a whole new world, right? All that music, Disney music is playing. Let it go. I really don't like Disneyland. Anyway, so firework explodes in the air at Disneyland. It says the air is the system. So I'm gonna draw, just a random circle right here, and this is the system. This is the air, and this is the system. Now, is the system going to absorb energy or release energy? Yeah, the air is going to absorb energy. Easy way to know that. Which one's hotter, the firework or the air around it? Obviously the firework, right? That's why it releases heat and light. And so the air is going to absorb energy, which means that if the air is a system, this is going to be an endothermic system. If we said the firework is the system, then it would be exothermic, right? But since we're saying the air is the system, it's going to be endothermic. Okay. All right. 6.12. A water bottle freezes in a freezer. Is this exo or endo? Okay. So if we have a water bottle, right, and it's freezing, right, it seems like it's going to be releasing energy, right, because it's going from a liquid to a solid. But what if I said the freezer is the system? The freezer is absorbing energy, right? But if you look at this, does it tell you what the system is? No. So here there is no answer because there is no system specified. I didn't tell you what the system is. So this was a trick question. You can't tell me if it's exo or endo because it doesn't tell you what the system is, right? Because if we said the water bottle is the system, that means it's exo because it's going to be releasing energy. But if we said the freezer is the system, then it's going to be endo because the freezer is taking energy from the water bottle. And so here we can't answer it because there is no system that was specified. Yeah, what's up? Yeah, there might be. So just keep that in mind. Make sure it tells you what the system is. It's okay if it doesn't tell you the surroundings, but it has to tell you that what the system is, or you can't answer it. Okay, good question. Okay, last thing before we finish up this section, there are two things you guys need to be aware of. The first are state functions and the second are process functions. Now, state functions, they are properties or measurements that describe the system as it is right now. Good way to think about it is that you can measure it without changing the system. Okay. So these are things that you can measure without actually changing the system. So things like pressure, volume, temperature, density, the energy inside, the change in and how the energy changes. But you can measure these without you actually changing the system. Okay, but there are process functions that tell you how the system got to its present state. So things like heat, work, things that change the system in and of themselves, you can only measure these by changing the system. That's what a process function is, okay? There's not a lot of questions on the AP test about this, so I'm not going to go too in depth, but just know that state functions, you can measure them without changing the system directly. I know it's kind of weird because it says change in energy. And so it's like, how can you get that without changing it? But it's how the energy changes in the system without you affecting it. But things like process function, you only measure the heat by adding heat or doing work. And so those are process functions. Okay. Not going to spend too much time on that. There's more in the book if you guys want to read up on it, because I know that you guys are all reading the book, right? Yeah, what's up? Great. Yeah, so there are things you can measure without actually changing the system. Okay, so like pressure, volume, temperature, the mass, right? How heavy something is, things like that. Alrighty, now we're gonna get to the real, I guess, meat of this unit, and it's this concept called enthalpy. And this is what we do a lot of the stoichiometry with, okay? Because, you know, I know y'all love your stoichiometry. Okay, so enthalpy is a measure of heat flow for processes that occur at a constant pressure. So basically it tells you, hey, is the system releasing energy or is it absorbing energy? The caveat is that we need to keep it at a constant pressure. Okay, this enthalpy value can change depending on the pressure, but it's just talking about, does it release or gain heat? Okay, so the symbol for enthalpy is capital H. Okay, so delta H is the heat gained or lost at constant pressure. So if it's a positive value, that means it absorbs energy. Okay, if it's a negative value, it releases heat. Okay, so you can think of them as endo and exo. Endo is a positive H and exo is a negative H because it's releasing energy. Okay. All right, so I'm gonna try a couple of the problems with you guys, and just so that you guys get a feel for what enthalpy is, and then after that, I think we're gonna start the stoichiometry real soon with this. Okay. All right, so let's try 6.13. So it says there's a container that contains ammonium nitrate, water, and mostly unreactive gases. Okay, so we got this container, and then we got ammonium nitrate, NH4NO3. We got some water in there. I'm pretty sure this is a solution. And then we have some gases flying around, okay? But it says that they're unreactive. They don't really do anything. Okay, the ammonium and nitrate and the water, they react, and then the container contracts. Okay, so the container gets smaller. Okay, so after they react, the container gets really small. Now I want you guys to figure out, hey, did the system gain energy or did it lose energy? Okay, so what's the delta H? Was it positive or negative? Okay, and then B is just the explanation. How do you know? Okay, did this system, did it gain energy or did it lose energy? Okay. So take about a minute. You can talk with the person around you. Okay, but did the system gain energy or lose energy if it got smaller? Another way to think about this is if you heat something up, does it get bigger or does it get smaller? And so if you cool something, does it get bigger or does it get smaller? Never mind, sorry. Guys, you can all figure this one out. Oh my God. Okay. Dude, I should have paused the recording for that, but hey, it's anatomy, okay? I'm not insinuating anything wrong. It's just an anatomical process. Okay, y'all know. Sorry, ladies, I'm not a lady, so I can't really relate. As soon as I said that, all the guys were like, yep, I know the answer. Guys, this is how I passed chemistry, though. This is how I got my degree. I just thought about stupid things like this. Yeah. It's whatever it takes, man. Whatever. Hey, C's get degrees. Alrighty, guys. So let's take a vote. The system got smaller. Who thinks that the system gained energy? So everyone thinks it lost energy? Yeah, the system lost energy, right? All you men should know that when it gets colder, things get smaller, they contract. And so it's going to be a negative enthalpy change. Okay, how do we know that? Because when the temperature decreases, so when the temperature goes down, things contract. Okay, if you wanted to get real technical, you could have been like, oh, if we decrease the temperature, that means the pressure of the gases would decrease as well. And so if the pressure gets smaller, that means the volume of the container is going to decrease as well. So, I mean, you could have gotten that technical like that. But it's sufficient to say, hey, when things get cold, they generally get smaller. Generally, yeah.
I wrote it down, but because similar to ice, it becomes more dense than it.
So ice is actually an exception because ice actually gets less dense. Water is weird because you know how when you cool something down, it gets smaller. But ice, when we go from liquid to solid, it actually gets bigger in the ice. That's why if you freeze something, it dies. It's because you have water in your cells. And so if you freeze the water, all of a sudden it goes and it rips up your cells. And so that's why freezing something kills them. It's because of the water inside the cells. I know, fun, right? All right, let's go to 6.14. So a lot of this is going to be conceptual again, but let's look at this system as well. Okay, 6.14. Okay, so you got a cylinder that contains butane and oxygen gas. Okay, and you got the formulas right here. This is going to be butane, and this is going to be oxygen gas. Okay, the system is perfectly insulating, so you're not losing any heat. Yeah, what's up? Yeah, go ahead. Okay, and then a spark causes the butane to combust. Okay. So based on the chemical reaction, is this cylinder going to expand or contract? Okay, so just think about it. You got a cylinder. If any of you guys are familiar with like engines, this is how engines work basically. You put, you know, your gas in there, and then it's in like the cylinder. Okay, this is going to contain your butane and then your O2, and then there's going to be a spark, and it's going to combust, and it's going to make these carbon dioxide and water. Okay, is the cylinder going to expand or contract? Is it going to get bigger or smaller? Okay, that kind of tells you the other two. Okay, so think about that. I'll give you guys 45 seconds for this one. Because it is kind of easy. If something combusts, right, is it going to get bigger or smaller? Yeah, if something goes boom, does it get bigger or smaller? It's okay, man. C's get degrees, and degrees get you jobs. Alrighty, guys. So let's just think about this logically. If something combusts, when you blow something up, does it expand or contract? Yeah, it expands, right? That's why when you watch those movies and a bomb blows up and the guy starts flying away, Mr. O flies away when a bomb blows up, it's because it releases energy into the gas around you, and then it causes the gases to expand. It pushes it away, and that's why people go flying when they're they don't get hit by the bomb directly. Okay, so it's going to expand. Okay, that's what combust means. Combust means burn, blow up, something like that. Okay, so it's going to expand. So if it's expanding, is it going to be endo or exo? Yeah, it's going to be exo. The system is going to be exo. And then the enthalpy change, is the delta H going to be positive or negative? Yeah, positive. Okay. There is actually another way to think about this. If you guys notice, they're all the same state of matter, right? They're all gases, right? Now, if you look on the left side, on the reactant side, how many moles of gases do you have? Not two.
Wait.
Moles. You have two different chemicals. You have 2 moles of butane. You have 13 moles of oxygen, right? So you have 15 moles of gas, right? Okay, if you look on the product side, how many moles of gas do you have? You have 18 moles. Now we know, even though this isn't at STP, that the volume of a gas depends on the temperature, right? So remember Avogadro's law? Okay, the moles of gas depends on the temperature. So if we increase the moles of gas on one side, that means we're also going to have to increase the temperature. And so that's how another way we can know that this is going to expand. Okay. All right, let's move on. And now we can actually talk about chemical reactions. Okay. So we can talk about enthalpy of a chemical reaction, and an easy way to think about that is the energy, the internal energy of the products minus the energy of the reactants. So how much energy do the products have minus the energy of the reactants? If the products have more energy, that means the system gained energy, right? Because we went from reactants to products. Okay, so the delta H that accompanies a reaction is called the enthalpy of reaction, and we do HRXN because reaction, right? Reaction. And so here's an example of an enthalpy of reaction. You have hydrogen gas and oxygen gas, and when you react them, they make water. And when you make water, it also creates energy. It releases energy. So this is a way I like to think about it. When the delta H is negative, that means that energy is a product. Energy is produced in the reaction, okay? So since delta H is like this, we can actually rewrite the equation like this. 2 moles of hydrogen gas plus oxygen gas produces 2 H2O, but it also produces 483.6 kilojoules of energy. Okay, so when we do our stoichiometry, you can actually use this value from the chemical equation. Okay, conversely, if it's an endothermic reaction, if it's a positive H, we would put the delta H on the reactant side. I'll show you guys more of that in a sec. But easy way to think about that, if delta H is negative, that means energy is a product. Okay, if the delta H is a positive value, the energy is a reactant. Okay, so depending on the sign, the positive and negative sign of the delta H, it's going to tell you whether it was a reactant, whether you needed it to start the reaction, or if it was created in the reaction. Okay. Any questions about that? Make sense? Yeah, so there's all these different terms like internal energy, enthalpy. Easy way to think about it is just energy, heat, temperature, things like that. All right, let's move on. So you're gonna need to know 3 things about thermochemical equations. You guys don't need to memorize these per se, but be aware of these things. So enthalpy is an extensive property. Okay, what does that mean? It means that it has a rate, it goes based on ratios, okay? So if you take a look at this, this first reaction, we have enthalpy change of negative 890 kilojoules, okay? It releases energy. But if we multiply everything by 2 in the reaction, right? You double the methane, you double the oxygen, carbon dioxide, and water. You also need to double the change in enthalpy. Okay, so the point is extensive just means that it scales up proportionally with the reaction, okay? All right, the second thing is the delta H for a reverse reaction is equal in magnitude but opposite in sign. Okay, what that means is, let's look at this equation again, the same one. CH4 plus O2 makes carbon dioxide and water. It releases 890 kilojoules. But if we wanted to go backwards, right, we have CO2 and H2O here. But if we wanted to take CO2 and H2O and make it into the reactants, CH4 and O2, it would have the same number for the enthalpy. It would just be reverse in sign, positive and negative, okay? So that's basically what that means. You can go the opposite way in reactions. Yeah.
So like if we wanted to like break apart this sort of like solution, I guess.
Mhm.
You can do so.
Yes. All right, and then last but not least, the delta H, it depends on the state of the reactant and products, okay? So you need to know what the state of the reaction is, right? Because, for example, if I have H2O liquid and H2O gas, right? If I change H2O liquid into H2O liquid, I didn't really do anything, right? It's still liquid, there's no change. But H2O liquid to H2O gas is something completely different. Here, we're going to have to absorb some energy. Okay, so just keep that in mind. When we do these thermochemical reactions with enthalpy, we have to specify the state of matter. Is it solid, liquid, gas, or is it aqueous? Okay. Again, you don't need to memorize all that. I'd say the biggest thing is this one right here. This is the concept that's going to help you the most on the test. Just knowing that it's the same value, but just opposite in sign when we go backwards and forwards in a reaction. Okay. All right, let's do some stoichiometry. Okay, so you have that big, ugly equation for you up there. I've balanced it already, so it's easy for you guys to do. Now, before we get started, I want you guys to take a look at the delta H. Okay, so for the delta H, is energy being released or is it being absorbed? It's negative. I'm hearing it whispered. Yeah, it's going to be released, right? Because think about it this way, the Mr. O example, okay? I am lifting something really heavy with very long arms, right? Okay. If I use energy, right, I have to use energy in order to lift that weight. If I'm using energy, am I absorbing energy or releasing energy? I'm releasing energy. Okay, I'm releasing energy. If I'm releasing energy, okay, is the energy in my body gonna be positive or negative? Yeah, negative, right? If, when you guys play sports or run or climb up the stairs here, right, you lose energy in your body. That's why you get tired. And so same thing here. If the value of H is negative, that means the energy is going to be released. This is exothermic. Okay, now if the energy is being released, is energy a reactant or is energy a product? It's going to be a product, okay? So make sure you guys memorize that. Okay, if the energy is released, you are making energy. You're releasing energy into the surroundings, which makes energy a product. Okay, so I can actually add on the product side plus 331.20 kilojoules of energy. Okay, so this is actually part of the balanced equation. Okay, so here we are going to do a little bit of stoic. And so what is the enthalpy change for the reaction above per mole of CO2? Okay, so if you guys ever hear the word per or see the word per, what number does that equal to? Yeah, 1. Per always means 1. So we're going to, our starting number is going to be 1 mole of CO2. Okay. So we need to set up an equation. I don't want moles of CO2. I want energy. I want to find energy. So I'm going to put energy on the top of the equation. Now, this might be weird because you're like, hey, like this is a chemical equation. Why are you putting energy in there? But we said that energy is released. So what we can do is we can actually rewrite this equation like this. Since energy is released, energy is a product. So I can actually write the equation like this, where I have energy on one side of the chemical equation. I have energy on the product side. So I can plug in my numbers from the chemical equation. How many moles of CO2 do you see in the chemical equation? 4. Now for kilojoules, what value do you see? Yeah, 3,120 kilojoules. Now it's on the product side, so we're releasing it, so it has to be negative 3,120. Okay. And then from there, pretty easy to solve that out. You just need to cancel your units, moles of CO2, and then that'll give you your value in kilojoules. So take a second to solve that out, and then we'll write it on the screen, and that'll be your answer. Alrighty, guys. So calculations should have been pretty simple. All you need to do is you can skip the 1. You just do 3120 divided by 4, and you get 780. Just make sure you don't forget that negative sign because we did release energy. So the answer here is every mole of CO2 that we use in this reaction, or that is produced in this reaction, there's going to be 780 kilojoules of energy being released. Okay. So the point of this problem is that energy is part of the chemical equation. Okay, you can put it on the product or reactant side. Just be careful with the sign, positive and negative. All right, part B. Do the reactants or products have a higher enthalpy? Okay, so easy way to think about this is the example with me and the weight. Okay, so if I start with the weight on the floor, okay, this is before the reaction because we said we're releasing energy, right? And then we're going to a system where Mr. O raises the weight above his head, okay? So just think, let's say my body, right? My body is the chemical, is the system. Do I have more energy before I lifted the weight inside my body, or do I have more energy after? Okay, I have more energy before, right? Because before the lift, probably I'm ready to go. I have calories in my body to fuel it, so I have more energy inside my body. But once I lift it, what am I like? I'm like really tired, right? Because it's above my head. So I'm gonna have less energy inside my body after I do the lift. And so same thing here. We're releasing energy. We're using energy. And so here the reactants will also have more energy. Okay. So the reactants have more energy. And how do we know that? It's because the delta H is negative. If the delta H is negative, that means they used energy. The chemical reaction released energy, right? So if I got rid of energy, that means that there's less energy in the products, which means that the reactants will have more energy. Okay. Does that make sense? So again, for this unit, you have to be very careful about what you're describing, the system and the surroundings. Okay. All right. And then can you guys see part C on the bottom or on your screen? Okay. Just because I want to show you guys this equation while we do this problem. Okay, so if we have liquid, this is ethane. If we have liquid ethane instead of gaseous ethane, because if you take a look at it here, we have gas, but let's just say this is liquid. And here you guys kind of have to use creative thinking. But if we use liquid instead of gas, do you think the change in H, will the number get bigger, smaller, or will it stay the same? And kind of a weird question, but right now we used the gas. Okay, so we used gas ethane, and we said that the delta H was negative 3120 kilojoules. Okay, if we use the liquid, God bless you. If we use the liquid instead, what do you think will happen to the delta H? Will it get bigger, smaller, or will it stay the same? Okay, so this is kind of a weird problem, so I'll give you guys a minute to try to think about that. Okay, I want you guys to think, if we change this into a liquid, is the amount of energy that was released going to get bigger, smaller, or stay the same? Okay, so take a second to think about that. I know, people are leaving me. They're so sick of me now. It's the fart jokes. As soon as I made the fart jokes, people started leaving faster. I should have just started farting. You guys would have all left. Close the door, turn off the AC.
What would happen if everyone like dropped out?
Huh?
What would happen if everyone dropped out?
Good question. You guys want to all try it? Just to see what happens. I've never been in that situation where I lost everybody.
There's always one.
I know. There's always one left over. I think it's good. It's good for their mental health. It's too much work in this class.
I enjoyed the job.
Okay, let's come back together and discuss this. So who thinks that the delta H will increase? Be loud, be not loud and proud. Raise your hands high and
It will require more
proudly.
energy.
Yes. Okay, so Ethan, why do you think the magnitude of H will increase? Yeah. Don't laugh at him. So you're taking in more energy to throw it away?
No.
Any increase people want to take a shot at it? Yeah.
I think that the amount of energy required to have the product and product
Mm-hmm.
would increase because if it's a liquid, that means it requires more to revert back to a gas.
So a liquid requires more energy to turn into a gas. Okay, that statement is true. But we'll try. We'll listen to what other people have to say. Who thinks it'll decrease? Who thinks less energy will be released? Yeah, Millen, you want to take a shot at it? Mm-hmm. So you're not going to need as much energy to change it from a. Okay, I see what you mean. And then Evelyn, did you have an idea different than that, or did you guys collaborate? Mm. Okay, for sure. Anyone think it'll stay the same? And the rest of y'all, oh, you do? Okay, why do you think it'll stay the same now? Same properties, okay, even though it's different state of matter. Okay, dude, you guys thought this really through. These are good ideas. So it's not all of them. There is one right answer, guys. There's always a right answer. Okay, so you guys all brought up your reasonings are all correct. So you guys are basing it all on evidence, which is good. But let's just think about this, and I think you guys will see the correct answer as we're going through. Okay, so let's say this is the reaction. Okay, so I'm just going to draw a box to show that this is the reaction. Okay, and in this reaction we have gaseous ethane. Okay, and then in this reaction we have liquid ethane. Okay, now everything you guys said was true. Gases have more energy than liquids. Liquids take more energy to break apart. They still have the same properties because they're gas and they're still the same chemical. But if you take a look at this problem, what we're looking at, okay, delta H has to do with the energy inside of the system, okay? So we said earlier, I think Evelyn said that gases have more energy, right? Gas has more energy than liquids. Man, I should not write it like that. Okay, gases have more energy than liquids. Okay, and liquids have less energy. It takes more energy to break apart a liquid. That is very true. But if you take a look at this system, are we putting energy into the system overall? No, the system is losing energy, right? And so it doesn't matter if it takes more energy to break apart a liquid. This is only talking about the energy that's lost from the system. So since ethane, the gas, has more energy to begin with, if we use a liquid, since liquids have less energy, that means that there's going to decrease. The delta H is going to decrease because it has less energy to begin with. Okay, so gases have more energy than liquids, right? So if we run this reaction with a liquid, there's going to be less energy for the liquid to give. And so it's going to release less energy. So think about it this way. Okay, let's say me versus like, I don't know, Steph Curry was on a basketball court, right? Steph Curry has more energy, right? He can shoot the ball better. So he's going to be able to produce more energy, produce more points than I could. It doesn't matter if we're both human, right? He just has inherently more energy, right? So he's going to be able to produce more than I can. And that's the same thing here, okay? The gas has more energy to begin with. So if we use a liquid instead, if you put Mr. O on an NBA team, that's going to be like 0 points for the whole game, right? And so there's going to be less production because it has less energy to begin with, okay? That one was kind of a tricky one. But again, always determine what the system is and don't deviate from the information that they give you, okay? All right, we're going to take, yeah, what's up? Uh-huh. That's a good question. No, it'll stay the same because we're still a combustion reaction because we're reacting with O2. The products will stay the same, but even if we use the liquid, but it's just that the amount of energy release would be less. Any other questions? That was a good one. All right, you guys look like you're falling asleep. I'll give you guys 6 minutes, a 6-minute break, and then we'll come back together and move on, I think, to the actual Stoich problems. Yeah, okay. All right, so let's go to 6.16, and this is going to be the actual Stoich. Hey, God bless you. All right, so part A, first thing we want to figure out, is this exo or endo? What do you guys think? Okay, it's endo because the delta H is positive. Okay, so we're going to be absorbing energy. This is going to be endo. And the reason why is because delta H is a positive value. Okay, now, if delta H is positive, is the energy going to be a reactant or a product? Yeah, energy is a reactant. Dude, my neighbors are so weird. I got a peak and I got someone playing the flute and the trumpet. Sometimes he plays drums. I'm like the most boring person on this floor. It's weird. Thought I was weird. Anyway, okay, so energy is going to be a reactant, so just keep that in mind. Next, we have the actual Stoich problem. It's asking us to calculate the amount of heat. So since we're looking at heat, we're going to be looking for energy, so probably in kilojoules. So you want to end the problem with kilojoules. Okay, you want to find the kilojoules when 10 grams of nitrogen gas reacts with excess oxygen gas at constant pressure. So your starting number is 10 grams of nitrogen gas, this is N2, and you want to use this number to calculate for the energy, okay, for the heat transfer. Okay, so this is basic stoichiometry, so I'm actually going to give you guys about 2 minutes to try it out. Okay. Use the chemical equation, use what you guys know about molar mass. Set it up like a normal Stoich problem. Just try to get rid of the units you don't want and end up with kilojoules, okay? Take a second to try that, or take a minute, maybe a minute and a half, and then we'll go over it together. What the heck is he playing, dude? Is that the SpongeBob?
It sounds like it.
Oh,
Oh, no worries. No worries. I really wonder, does he just play music while his kids are working? So interesting. Actually, that makes sense. I play basketball while people are working, so. Huh? Flute is hard. Music is hard. I have no musical ability. Nah, it's still hard. I was made to do math. Actually, I was made to be a pro gamer. I failed my Korean heritage.
Still good.
No, I can't. Not good enough. Trash at everything. I'm trash, dude. Everybody that I play with online says I'm trash.
Oh, what game?
Every game I play. I play StarCraft a lot, League. The typical Korean games, dude. I try to be what my genetics told me I should have been, but I couldn't make it. I trolled too much. No, I'm not gonna play Minecraft. It's past my generation. It is. The game I played the most in my life, probably Maple Story.
Huh?
Do you guys not know Maple Story? Yo, that game was fire. It was so fun because it was so easy to hack. So we would just DOS people off the server. This is back in the day before, like, I don't know, before there was like good client like support. So we would like, there's like a lot of dumb stuff going on. Like there'd be like a lot of people would be like, oh, drop your best item, and then whoever can run to it will pick it up. Like, but I'll give you a 2-second head start. But somebody would hide on the map and then steal their item, and then we would split it. Anyway, it's bad misro. All right, you guys all done? All right, so we got 10 grams of N2. So what we're gonna do is we're gonna set up a fraction. We wanna use the chemical equation because like we said, energy is a reactant here. So we wanna turn this into moles if we wanna use the chemical equation. So we're gonna take grams of N2 and we're gonna turn it into moles of N2. Now, if we have grams and moles on the same fraction, where do we get the numbers from? Molar mass, yeah. Okay, so you go to your periodic table, look at nitrogen, 14 times 2 is 28 grams per 1 mole, and then our grams will cancel out. Okay, then we're going to move on to the chemical equation. We want to turn moles of N2, and we want to turn it into energy, so we want to turn it into kilojoules. You go to the chemical equation, you see, oh, there's no number in front of N2, so it has to be 1 mole. And the amount of energy that is absorbed is going to be 67.6 kilojoules. And we keep it a positive number because the energy was absorbed. Okay, so all we need to do to finish it up is to plug and chug that into the calculator. So we got 10 grams of N2 divided by 28, which is the molar mass, multiplied by 67.6, and that'll give us 24.143 kilojoules. Oh, that is a SpongeBob song. Okay. And we know that this is correct because again, this is an endothermic reaction, so it should have a positive delta H. Okay. So energy basically acts the same as like a chemical reactant or something inside these thermochemical equations. You just need to use it the way that you normally would. Okay. It's actually easier because we can skip a step. We don't have to turn it into grams. Why are you guys laughing at me? Or is it the SpongeBob? SpongeBob? Okay, sure. You guys can laugh at me. I'm a weird person. All right. I want you guys to try this now. This one we're going in reverse. Now our starting value is 200 kilojoules. And I want you guys to find the grams of NO2 gas that are produced. Okay. So same thing we just did, we just have a different starting number. Okay, so try that out. See if you can set up the equation. And if it's hard, just struggle through it. A big part of this is figuring it out. And so try to figure out how to set up that calculation. Alrighty, I'll give you guys like 20 more seconds to finish that up. This unit's long.
Should start a phase from this chemistry course.
Nah, they can. I know they all play instruments. I have no musical giftings at all. Oh, that's mine. I could play a little, yeah. A little bit. Like I know 4 chords, 5 chords.
Hear me out. Most pop music is literally just the same.
I know. But see, the thing is, Mr. I just don't enjoy music.
You know,
Yeah, I used to dance, and that's the extent of music.
K-pop.
No, not K-pop. I used to break. No, I did not K-pop. I'll show you a video later. Dude, I can still smoke everybody here. I'll battle all of y'all. Anyway, you guys ready to go?
Yes.
Okay, so let's start with our starting value of 200 kilojoules. So we're gonna write 200 kJ. Now we don't want kJ, we want grams of NO2 gas. So we're gonna set up a fraction. Now it tells you here that it's gonna be 67.6 kilojoules per how many moles of NO2? Yeah, so we'll set up a fraction with kilojoules and moles of NO2. Okay, then we want to turn that into grams. So we're going to do 1 mole of NO2, and then we're going to find how the molar mass of that. And I think that's 44, 46. Thank you. CO2 is 44. It's going to be 46 grams of NO2. Okay, so we're all done with the equation. We just need to plug it into the calculator. We start with 200 multiplied by 2, divided by 67.6, multiplied by 46. And then we're going to get 272. So it's going to take 272.189 grams of NO2 in order to produce 200 kJ of energy. Okay, yeah. No, because this problem is asking for specifically NO2. So yeah, if you found N2 that you're not asked giving what the question asked for, it's asking for grams of NO2, so you're supposed to look for NO2. Yeah. Oh, okay, I see what you're doing. Yeah, if you could use that value, as long as you get the same value at the end, you're good to go. Yeah, no, sorry, I misunderstood what you said.
Oh yeah.
Yeah, because it's the same, yeah, conversion, so you'll still get the same value. So the interesting way to do it, but glad it works. Oh, it worked for you too? Okay, well, I'm glad it worked for you guys. Yeah, like I said, there's multiple ways to do these problems. It's all about creative problem solving. And if that makes sense to you, by all means, go ahead and do it. Alrighty, guys, last question. Okay, last question that we're gonna do today. Okay, 6.17. Now, let's go through part A quickly. So part A, super easy. This is exothermic. Okay, and the reason why is because it's a negative delta H. That means the energy is going to be, the energy is going to be a product. Okay, so I want you guys to do part B. We'll actually finish part C and D next time that we meet. So if you guys finish part B, we are all done. Now be very careful with this because it's going to be a little bit different than just regular stoich, okay? Huh? Probably upstairs speakers. I'm not sure. Too many sounds. Alrighty, guys, I'll give you guys maybe 2 more minutes to work on that, and then we will double check our answers before finishing up for the day. Alrighty, guys. So for the sake of time, I'm gonna start going over this. If you guys are still finishing up, though, please feel free to finish up. You can ignore me for a bit and just check your answers at the very end. Okay. Now, what you should have noticed in this problem is that you have 2 different starting values, right? Which means we have to do stoichiometry 2 times. Does anyone remember what type of problem this is?
What's the
Yeah, limiting reagents / excess, right? And so we need to figure out which one limits the reaction, because that'll let us figure out how much energy is actually made. Okay, so we're gonna start with the 20 grams of sulfur. Sulfur is 32 grams per 1 mole. So we're gonna set that up. And then after that, we're gonna use the balanced equation right here. It's 1-to-1, so it's gonna be 1 mole of sulfur is gonna produce 296 kilojoules. And so that's how you'll set up that fraction, right? Or that process. Okay, same thing for oxygen. Now, oxygen is going to be 32 grams of O2 gas per every 1 mole of O2 gas. And the same thing right here. We got 296 kilojoules and per 1 mole of O2. Now, if you guys take a look at this, without even solving both of them, you can already tell which one is going to limit the reaction, right? Yeah, sulfur is going to limit the reaction because if you see, the molar mass is the same, 32 and 32, 296, 296. We know the smaller value is going to be the one that we use, right? So obviously sulfur is going to be the limiting reagent because it's small. 20 is smaller than 25. And so we know that this one is going to run out first. So I don't even need to do the math for this one. I just need to do the math for the first one. So we got 20 divided by 32 times 296. And just make sure you guys make that negative. And so that's going to be a final answer of negative 185 kilojoules. Okay. So again, we didn't have to do the second one because we can see that the values are the same. This fraction is the same as this one. This fraction is the same as this one. 25 is smaller than 20. So we already know this is going to make the bigger number. So this is going to be your excess. So we just need to do the first calculation. Okay. And so these are easy ways to kind of save time on the AP test and the exams, just so you don't have to do any extra work, because as we know, every minute is precious. And so that's the easy way to just kind of check your numbers. All right. Any questions? All right. So we'll do some more thermochemical stoic next time we come back. You guys can just start wrapping it up. Now, if you want to check your answers to the exam, I will have them posted on Canvas. And I have it up here. But this recording will be on YouTube as well if you want to take a look at it.